G'day guys, this video is going to look at chapter 22, the 1-star questions at the end. Let's get into it. So our first 1-star question reads, for question 17, what is the electric current in the following cases? Sorry, sneeze coming on. Apologies. Okay, so what is the electric current in the following cases? So in all these we're trying to find I equals I don't know. Let's look at A. Now A, we're given two numbers. We're given a 20 coulombs and we're given 5 seconds. And now coulombs, remember, is the value of charge, symbol is Q, and seconds is the unit of time, symbol T. And if we have a look at this, we need to relate Q and T to I. Well, that's our definition for current. Current is equal to the amount of charge passing a point divided by the time. So if 20 coulombs passes a point in 5 seconds, that's going to give us 4 amperes of current. Look at the next one. Now we've got Q equals 5 coulombs, time equals 20 seconds. Again, check these in. I equals Q over T equals 5 divided by 20, and that would equal 0.25 amperes. Okay. Alright, let's have a look at C now. C, if you're sort of fall, this one can be a little bit of a trick here, because if you just fall into the habit of, oh, I take the charge, I divide it by the time, you might go 200 divided by 3, which would be wrong. So C, we have Q equals 200 coulombs, but time equals 3 minutes. That is not our SI unit. We need to divide it by 180 seconds. So I equals 200 divided by 180, 20 divided by 18, 10 over 9, so it's going to be, 1.1-ish. So 200 divided by 180. Yeah, 1.1 exactly. 1.1 recurring anyway. Okay, so there's 17. Let's go on to 18. What is the energy gained by a charge of 18 coulombs when it passes through a source of EMF of 12 volts? Okay, so let's put down our numbers. We have two numbers here. 18 coulombs is our first number. 18 coulombs. And we have a 12 volts. Now, volts is the unit of voltage, symbol is V. Coulombs is the unit of charge, symbol is Q. And let's go back to the question, what is the energy gain? So we're looking for some energy. Now we might write E for energy, but a lot of these equations are using W for work. Okay, and so sometimes that can be a bit of a trick. They might ask you about the energy. We think about, well, energy is joules, but work is just another way of talking about energy. Okay, so you've got to be aware of that. And we do have the equation work equals QV. It's going to equal 18 times 12, which would equal, let's see, 10 times 18 is 180, 2 times 18 gives us 36, so that would be 216 joules, and the text in this case is rounded off at 2.2 times 10 to the 2 joules. Okay, so they're rounded, but yeah, same thing. 19. If a 1.5 meter length of resistance wire has a resistance of 1.9 ohms and the wire has a diameter of 0.9 millimeters, calculate the resistivity of the wire. So let's draw our wire, which we assume that a wire is a circle. I mean, every wire that I've ever seen looks to be a circle to me, and that's 0.9 millimeters. So D for diameter equals 0.9 times 10 to the negative 3 meters. That means radius has to equal half that, and if we divide 0.9 by 2, yep, 0.45 times 10 to the negative 3 meters for radius. Let's go through the rest of the stuff here. We have a 1.5 meter length, so length equals 1.5 meters. And we have a resistance R of 1.9 ohms. Okay. And the final thing is it's asking what is the resistivity. Now resistivity in that one formula that really deals with this is given the symbol rho, kind of a slopey P that doesn't quite connect up. So if I look these three things, the formula that kind of stands out to me is that resistance equals resistivity times length divided by area. And so we have two of these, and we're after this third one. We don't have area, but we do have radius. And remember that the area of a circle is equal to 2 pi r. Okay, so area of a circle equals 2 pi r. And r we have, so let's substitute that in. Resistance equals rho length divided by 2 pi r. Let's rearrange this. So I have a 2 pi r on the bottom. We're going to multiply that to the other side. So now I have 2 r pi small r equals rho L. And let's divide that L to the other side. So rho is going to equal 2 r pi r divided by L. Now the advantage of doing things like this where we're substituting a formula and then rearranging it is now I can just put the numbers directly in, plug it in my calculator, and I don't have any rounding errors. That can save us a bit of precision down the track. Don't feel that you have to do that though. I mean, if you solved for area first, you substituted length and area and got that to be a number, and then just divided that number over the top, you'll still be, within a thousandth of a decimal place more than likely. Okay, so remember, it's not the answer at the end that particularly matters. What matters is that you are able to show how you got to that answer, and as long as that sequence is making sense, then you're okay. Let's chuck in our numbers for that. Rho equals 2 times resistance, which was 1.9, times pi, times radius, which is 0.45. Wait, 2 pi r is the circumference, not the area. Ugh, I'm an idiot. My apologies. That should be pi r squared. Let's fix that up. Pi r squared, so there's not going to be a 2, that's going to be r squared. Let's get rid of that 2, that r is going to become squared. Let's get rid of that 2, this is going to be r 10 to the negative 3 squared, divided by our length, which is 1.5, and now that we've got all that, we can chuck that in a calculator. Now if you're using a older style calculator where you might have to be very liberal with the brackets, I'd recommend putting this bit in first, squaring it, multiplying it by these two numbers, and then dividing it by that number. So that's what I'm going to do. Now I'll try to do this visible for you so that you can see the process I'm doing. So first off, 0.45 exponential negative 3 equals, and I just like to hit equals just to make sure, and you see it corrects it to 4.5 times 10 to the negative 4. We want to square that answer, so it's got answer squared. Bang. Now we're going to multiply it by pi, shift pi, and then multiply it by 1.9 equals, divided by 1.5 equals, we finally get the answer 8.1 times 10 to the negative 7. So that equals 8.1 times 10 to the negative 7. Now what's the units that we've got here? So the units for resistance is equal to ohms. Pi doesn't have units, it's just a number. The units of radius squared, or radius is in meters, so that's going to be meters squared. And where length, so that's going to also be a meter. So a meter squared divided by meter, one of those meters is cancels, so that would be 8.1 times 10 to the negative 7 ohm meters. Okay, when in doubt, that's a bit wonky looking ohm. Okay, when in doubt, put the units into the formula and see what cancels off, because that's going to be your units. The formula has to match on units as well as on numbers. Okay, question 20. With the aid of a circuit diagram, so I'm going to draw a circuit diagram. Show how you might measure the operating resistance, R, of a single light bulb. We have a battery, an ammeter, and a voltmeter. So that's good. An ammeter and a voltmeter an ammeter and a voltmeter will measure current and voltage. If we have those two things through a piece of equipment, we know the resistance of it. We've got a battery, that's important, otherwise the thing wouldn't turn on. So let's draw our pieces. There's our bulb connected to our battery. Okay. Now, an ammeter must connect in series. So I'm going to put my ammeter before it. It doesn't matter if you put it before or after in this case. There's our ammeter. And a voltmeter must go in parallel. Okay, so it's going to go around, it's like it's hugging it. Okay. Remember, when two objects are in parallel, their voltage is going to be the same. When two things are in series, their current is going to be the same. Okay, and that idea to keep in mind that things in parallel have same voltage, things in series have same current, will help a lot with circuit diagrams down the track. So there we go. If we have it set up like this, we have to know the current, we have to know the voltage, and that will tell us the resistance of our light bulb. Pretty straightforward. 21. The accumulator of a car produces 12 volts. If the car lights at the sides and rear are each rated for 12 volts, but the two interior lights are only rated at 6 volts, how should the lights be connected, in series or in parallel? Okay, now, I don't know what an accumulator is. I assume it has something to do with charge, and perhaps it acts like a battery because it says it produces 12 volts, and batteries I know produce voltage, so maybe an accumulator is a battery. But if we actually read through the whole question, all we need to give as an answer is, are these things going to be in series, or are they going to be in parallel? So if you're looking at a question like this and you have absolutely no clue, it's a 50-50 guess. Write a word. Okay? If you get it wrong, you don't get any points. If you don't attempt it, you don't get any points. But if you write something, even if it's just a guess, at least you might have a shot at getting something. And that's important. Okay, so let's have a look at the things. We've got some lights at the side and the rear, and the two interior lights. How should the lights be connected? Well, it doesn't really tell us what lights they're talking about. Let's draw our battery. So we've got our battery, and that's at 12 volts. And we're told there are 4 lights. So we have the 2 lights on the inside. These are both rated at 6 volts. That means that they need to use up 6 volts of power, or 6 volts of voltage, as the current flows through them. Too much, it's going to blow. Not enough, it's not going to work. Okay, so it has to be 6 volts. And we have side ones at 12 volts, and we have rear ones at 12 volts. So these are the side, rear, and interior. Okay, so think about this. It's got to leave the battery, come back to the battery. When it gives off, it has to add up to 12. So if I leave here, I go to here, 6, 6, 6, back. 6 volts, 6 volt, that's 12 volts. Gives 12 volts, uses 12 volts. That could work. Okay, so these 2 bulbs, so interior lights, in series. Now this is a 1-star question. There's no complexity to this. It should be reasonably just a straightforward recognition, description, or identification type question. We've identified here that we've got 2 6-volt bulbs. If we're giving it 12 volts, they need to be in series. If we had set these up these 2 up in parallel, they'd both be getting 12 volts, even though they're only said they can handle 6. Now, when something says they can handle 6, it generally means it can go maybe up to 8. Right? That 8 is still going to burn it out really quickly, though. So it's not going to blow it the instant it ticks over 6, because then nothing would ever work. We'd be burning everything out pretty much every day. However, if we go too far under it, say down to 5, it's probably going to get pretty dim. 4, it might not even work anymore. So we need to make sure that these are getting what they're rated for. These 2 here could be in parallel to this system. So for example, I could then go from here to here and then back in, because now the path could either go here through to these 2 and then back, or here through this one and back. This is drawn in parallel to this. The drawing is not perfectly clear because the way I set these batteries, these light bulbs up originally, going left to right. However, I hope you can see here that this one is parallel to these 2, because it could choose to go this path, or it could choose to go this path. Same thing for this one. This one needs to be parallel to the other ones as well. Okay, because it could go this path, it could go this path, or it could go this path. Okay? We couldn't put these in series. The bulbs would either be too dim or they wouldn't work at all. They have to be in parallel. So the interior lights are in series. The external lights are parallel to each other, and the lights, or the interior lights in series. Interior lights in a series. Okay, so this question is really kind of vague to me. It doesn't expressly tell us which lights they're talking about. They said, how should the interior lights be connected? Then you know exactly what they're talking about. It doesn't. It's not really a great, well-written question that takes in terms that it's made very clear to you as the reader what you need to talk to them about. So a full response would sort of look like this. The interior lights must be in series. The external lights must be parallel to each other because they're both got to have 12 volts, and they must be parallel to the two interior lights who are also using up those 12 volts. Okay, 22. How does the resistance of a 60 watt 240 volt light bulb compare with that of a 25 watt 240 volt light bulb, which has the thicker bulb filament? So two things there. Let's ignore that second sentence. Let's just look at the first sentence. So we have two bulbs. Let's call them bulb 1 and bulb 2. You can call it B1 and B2 if you really want to. So let's have a look. For bulb 1 we have 60 watts. We have 240 volt AC main. Volt V for voltage, symbol is the V. Watt is the unit of power, symbol is P. Bulb 2, same thing, P equals 25 watts, and voltage equals 240. And in both of these we want to know what is the resistance equal to. Well, we have a formula that links these three things together. We know that power equals voltage squared over resistance. So for this one it's going to equal 240 squared over resistance is equal to 60. All that R equals 240 squared over 60. And we can do the same thing here. Let's call that R1. R2, let's sub those numbers in. 240 squared over 25. So let's just work out the resistance for these first. 240 squared divided by 60 gives me resistance 1 equals 960 ohms. And resistance 2 equals 2,302 ohms. So how do the resistances compare? That is a lot that is a lot smaller than that one. But the second part of the question asks is about diameter. What is the diameter, or what is the thicker bulb filament really? So it's asking for the thickness. So it's going to have something to do with these resistance. Let's look at our formula for resistance. Resistance is equal to resistivity, time length over area. So what assumptions do we have to make? We can assume that it's the same material. Okay? Assume same material. So rho. So rho 1 equals rho 2. So now we just care that resistance is proportional to length over area. What else can we assume? Think about the light bulbs you've seen. Aren't they all pretty much the same shape? Like if you look at different types of the really old globy type ones, and you may have some of those at home, the ones with the filaments on the inside, a 60 watt light bulb looks the same as a 50 watt light bulb, looks the same as a 25 watt light bulb. They all look the same in terms of how their dimensions, their size. So that would tell me then that the length of the wire is likely to be the same. Let's do that. Assume L1 equals L2. So now we just care that R is proportional to 1 over area, and because length is not changing. So what do we know about area? Well, area is proportional to radius, which is just diameter divided by 2, and diameter is thickness. how thick a wire is. Well, we're really asking what's the diameter of that wire. So let's look at this. If area gets bigger, resistance gets smaller. And remember, area equals pi r squared. So let's put that in then. Resistance is proportional to 1 over pi r squared. Pi is just a number, so let's get rid of that. It's that 1 over r squared. So if r increases, okay, gets thicker. Well, if this number gets bigger, this number will get smaller. If you're dividing by a bigger and a bigger number, and that number is going to be squared, your result is going to get smaller and smaller. If r increases, then r gets smaller. Alright, so we had a couple of formulas here. Our first was just to find resistance in the first place. Once we had resistance, we need to look at the physical properties of resistance because we're after thickness. So we wanted to use this formula and start trying to get rid of some of these variables that we're just going to assume is the same. Now, if length was different between these two wires, though, because we assumed that length was going to be the same, then this might not be true. Maybe a shorter, thicker wire might have a higher resistance than a longer, thinner wire. They're both linear proportions. It's just a matter that one makes it small, one makes it big. Let's go on. Question 23. In the pictures, so figure 22.29, so there are 3 pictures to the left there. Find the readings on all voltmeters and ammeters as well as the total circuit equivalent resistance. Okay, let's get into this. This one's going to take us a little bit of time to work through. A, we have 12 volts, goes into a resistor, goes into an ammeter, goes into another resistor, comes back, and there is a voltmeter across that resistor, and that one is 6 and that is 4 ohms. So let's work out the resistance total first. Resistance total. We have 2 in series. Resistance total is just going to equal 4 plus 6 equals 10 ohms. We know the total voltage. Voltage total equals 12. What would the current total equal? Because if we have a look at this, the current total in this case is going to be what goes through there, because it leaves here, goes through here, goes through here, goes through here, comes back to the start. It's in series, so everywhere around it in series should have the same current. And the formula for current equals V over R would equal 12 over 10 equals 1.2 amps. Okay, so 1.2 amps is flowing through each of these things. So if I just look at this resistor, we have that R equals 6, current equals 1.2, because we just worked out it's the same everywhere. We want to know what is the voltage. And remember the formula for voltage. Voltage equals IR equals 6 times 1.2 equals 7.2 volts. Okay, there's our first one. That one's reasonably straightforward. Let's have a look at the next. Okay, now we've got a 20 volt battery leading to a resistor with 10 ohms, up to an ammeter, up to a resistor of 10, a ammeter into another resistor of 10, and they have a voltmeter in parallel across both of those. Okay, again, it's asking for us resistance total, so let's start with resistance total. We've got these two here in parallel. Okay, so that's going to be a parallel rule. 1 over RT equals 1 over 10 plus 1 over 10. We're just adding the inverses or the reciprocals of all the circuits in parallel, all the pieces in parallel. And that equals 2 over 10. So if we flip it, RT is going to equal 10 over 2 equals 5 ohms. So if I was to redraw that, I'm not going to draw the ammeters and voltmeters. We're going to have our 20 volt into a 10 ohm around into a 5 ohm and then back. What do we do when they're in series? We add them, so RT equals 15 ohms. We know that voltage equals 20, and so we could work out the total current. And the total current, remember, is going to be whatever leaves the battery, goes through until it gets to here, and then it's going to split into two paths. It's not going, we can't work out what's at the path until a little bit later, but we can work out, well, what the current is here. Remember, I equals V over R, 20 over 15, which equals 4 over 3, or 1.3 recurring amps. Okay, so we know what's on A1, we know what this first one is equal to. We should now work out the voltage. Okay. Like, intuitively we can see, well, remember, due to the junction law, that whatever goes into this junction has to come out on these two paths. They've got the same resistors. We know it's going to be equal to whatever half of that is, but we can't write that. We have to prove that. So let's try to prove that. Here, this is going to use some voltage. We know the current through it, we know the resistance of it, we just don't know the voltage. So we know that R equals 10, current equals 1.3 because it's what's leaving the battery. So voltage equals 10 times 4/3 equals 40 over 3. And I'm going to leave it as a fraction because it's just going to be a nasty decimal. 13.3 would be our answer. We know the voltage that's getting used up, but the whole thing, the whole way around, has to use up all that voltage. So 40/3 gets used here. That means whatever this take away that number is going to be what's left over for here. Let's work that out. 20 take away 40 over 3 is going to equal the voltmeter reading, because that's what's in parallel across it. That's going to be the same as 60 over 3 take away 40 over 3, which is the same as our voltage. 60 take 40 is 20 divided by 3, and that's our voltage there going across the second bit. Now if we turn this into a decimal, we find that 40 divided by 3 is equal to 13.3, while 20 divided by 3 is equal to 6.6. Alright, and we can see then, because the resistance is a lot lower, it needs a lot less voltage than what this one here with 10 ohm resistance actually needs. You're going to push harder to get through it, basically. Let's go back up. We've only worked out one ammeter, we've worked out the voltmeter, but being as we know the voltage across this resistance, we can now work out the current again. So we have V equals 20 over 3. We have that resistance equals 10. We want to know what I equals. So we have that I would equal 20 over 3 divided by 10. That should equal, 200 over 3? 20 over 3 divided by 10. If we divide by 10, oh sorry, that should be 20, so that would equal 20 over 30 equals 2/3, or 0.67 amps. And if we look at this, that's 1.3, so 1.3 divided by 2 gives us pretty much close to that, because that's rounded off. That should be 1.3 recurring. 4 divided by 3 divided by 2 gives me 0.666666, so 6 recurring. And we can see then that that intuitive thing of just, we'll take that and cut it in half did match our answers, but we needed to show that it was going to be that answer, and that's for ammeter 2. Okay, let's have a look at C. C is a little bit interesting because there are now 2 batteries here. Let's have a look at our batteries. So we've got one battery and we've got another battery. Note that the batteries are facing different directions. We've got a resistor through to here. We've got this coming over here to an ammeter, which goes to another resistor and goes back, and they've put the voltmeter in parallel here. Okay, so let's work out firstly the total voltage. So this is 6 volts, and this is 12 volts. So let's assume, what we're going to do first is assume a direction of current. So I'm going to go with the 12 volts. I'm going to assume it goes to the right. It's going to leave the positive terminal. So it's going to go here, 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 and it gets to this other battery. We notice that the battery's in the direction. So it goes here, 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 back to here. So there's no argument. If this battery has been swapped around the wrong way, then we might have a bit of a problem. But we don't, so it doesn't matter. So the voltage total, though, in this case, doesn't equal 12 or 6. It equals 18 volts. The fact that the two batteries aren't next to each other doesn't matter. Okay? They're in the same direction. They're going to help each other out. The resistance total, well, the fact that there's these batteries between them, again, doesn't matter. The fact that there is a voltmeter in parallel in the middle of the circuit doesn't matter. It's just two 10 ohm resistors in series. So that's going to equal 20 ohms. So we can work out the current total as V over R, 18 over 20 equals 0.9 amps. And that is on ammeter 1. Oh, there's only one ammeter, I don't know why they called it ammeter 1, but they did. If we look at the voltage, we know the current flowing through here, that's meant to be 10, and that's meant to be 10. We know the current that flows into here, so now we can work out the voltage that goes across it then. So, current equals 0.9. We know that resistance equals 10, V equals IR, so therefore equals 0.9 times 10 equals 9 volts. And being as that's 10 volts, it's also going to be 9 volts. But we can see here, this one's leaving with 12 volts, but it's only using up 9 here, so it'd be down to 3. Gets to here, charges up with 6 more, and then so then 6 plus 3 is 9, and then it would use 9 there and come back as 0. If something leaves here, it would leave with 6, drop down to negative 3, gain 12 to get to positive 9, lose 9, get back with 0. And we go, well, again, negative volts. The reason is it's not just one electron leaving here, it's a whole bunch of electrons getting pushed by both things going on. So while the math can seem a bit weird, oh, it went to negative voltage, it still is correct. That was 23, 24. Why can birds touch overhead wires, but we can't when we're standing on the ground? I don't know how to draw a bird. There's my bird. And here's a wire it's standing on. So if we think about this, we have some current flowing on. Because we have it touching in two places, we would have basically the voltage being pushed this way is going to equal the voltage going that way. But what is the resistance of the wire compared to the resistance of the bird? Well, wire resistances are generally pretty low, especially ones designed for high voltage thing. So for a bird, the resistance is higher. Therefore, if resistance of bird is higher than resistance of wire, then no electrocution. Because the resistance across that small section is probably less than the resistance through an organic mean. The other way of thinking about it is that it is flowing through it, however it's not flowing across the heart, so it's not going to affect it as much. It may cause some muscle tensions, but it's up to birds to figure out. It's more likely to say that the resistance just is not enough, or not high enough, low enough, sorry, to make it worth the electricity's while. Okay, now 25, 26, 27 are all two-star questions. I'll in another video. We do have 28, 29 and 32 left. Let's do these ones. So we can try to put it all in one video for you. Okay, 28. Explain the physical and operational differences between a fuse and a circuit breaker as safety devices in household circuits. So for something like this, you'd be looking back through the textbook. Okay. I'm not asking you to understand the context of electrical safety in an exam. I'm asking you to be able to work with the equations, obviously, but this sort of understanding of operational and physical differences would be better suited towards an assignment. So let's just list off some things. So a fuse, the way it works is it melts. Okay? The fuse gets too hot, there's too much electricity flowing, the resistance builds up, that increases the heat, so there's more resistance, which increases the heat, and then the fuse melts. And so it's a one use, but it's also very quick. Okay, so a fuse will burn out really quickly if there is too much electricity, which is what happens when you short circuit something, when you electrocute something, in that there is too much electricity going. A breaker is like the things we have at the front of the lab. It just switches over. Okay, so when it detects that there is an electrical surge, a switch flips over, just go back and push the switch back. Kind of like how when the fans turn off in upper K block, I go into the prep room, I turn the breaker off, and then I turn the breaker back on. Oddly, that's still called a fuse box, even though it's not technically a fuse. This means it's got many uses. I don't have to replace a circuit breaker after it trips, I just got to switch it back off. But it is a little bit slower. Not like, so slow that you can see the differences really, but in terms of electricity and the speed of electricity, it is a little bit slower. So these are the operational differences and the physical differences. This is made of a high resistance wire that melts very easily. This is just made of some electrical current that's going to end up tripping a switch or setting off a switch. It's set up for one use versus many uses. This commonly comes in like a little glass tube with a wire going through it. These are very quick to act. These are very slow in comparison anyway, because of the way that they're designed. If you're interested in fuses versus circuit diagrams, just type circuit breakers, type it into Google, you'll find a lot of information on it. Okay, another explaining one. Explain the precautions that are required if any metal-framed appliance is to be connected to the household main supply of electricity. Complete a circuit diagram. Now, we're not going to do a circuit diagram because we're not worried in circuits in that level of depth. What we're going to do is a very rough diagram, though. So let's think of something that would be metal framed. The one that stands out the most to me is a toaster, or even a kettle. Like my kettle has a metal case around it. Metal conducts electricity, so if there's a problem with the wires inside, that case on the outside is going to start conducting 240 volt AC. Think about the videos we saw. Electro Boom could electrocute his tongue with about 6 volts of AC current before it got really painful. If it crosses your hand through to your feet, because if you're touching a live wire, it's going to go through your hand and down into the earth through your feet. While the resistance is higher, I doubt it's going to make it to 240 volts. I do believe I've got a video of him touching with his hand different types of levels of AC and DC voltage. So let's use a jug or a kettle, e.g. kettle. And my kettle kind of has a plate on the bottom with a little plug that the kettle sits on, and then it's got the kettle, and it's got its spout, and it's got a kind of handle on top. So this is where the electricity, water on the inside, etc., etc. Okay, when we look at and have a look at the ones around your home, you'll see that most of your power plugs, if not all of them, have 3 plugs on them. The top left one is the active. That's where the electricity comes in. The next one is the neutral. Nothing goes in it, nothing leaves on it. And the next one, the bottom one, is called the earth. And that earth wire connects to a metal pole that goes deep into the ground somewhere on your property, probably under the house somewhere. Now think about what we originally learnt about electrons and electricity way back at the start of this unit, in that electrons like to flow from areas of high charge to low charge. And if I have this thing having a short circuit, then there's going to be a build-up of electrons on this metal casing. Because remember, electrons spread to the edge of an object. They don't go through the middle, they go right to the surface of it. So this thing's going to be covered with electrons. what happens if you touch it? It's going to go try to earth itself through you. However, if there is an earth path set up on here, then it will flow through that earth. So normally what's happened is this wire that runs into it, it will have a touch, some sort of contact, and that will have an earth wire that goes through the earthing system in your house. Okay, so that, let's write that as an explanation. The metal case must connect to earth wire so any charge can flow safely to ground. Literally into the ground, that's why it's called a ground. What sort of material do we want? Well, we want something with a lot less resistance than what goes through a human body. Okay, so we want something with very low resistance metal, that way we get all that current flowing away. And that's what we use. And finally, question 32. Draw the circuit diagram that represents the following description. Okay, so this is a long description. Let's go through it first once. Two paralleled 50 ohm resistors are connected in series with three large resistors of 100, 200 and 250. The assembly is connected to a 20 volt battery and an ammeter to measure the total circuit current. A voltmeter and ammeter must be used to measure current flow through and voltage drop across one of the 50 ohm resistors when the main circuit switch is closed. So, we have 50 ohm resistors times 2. I just can't draw omegas when I rush. We had a 100 omega, a 200 omega, and a 250 omega mentioned. There is a battery, 20 volt battery. There was a voltmeter and an ammeter. Let's hang on. Ammeter measured total circuit current, so there were 2 ammeters and a voltmeter, and a circuit switch, so there had to be a switch. So we need to use all these in our diagram. Thankfully we don't need to do any math on it, we just need the diagram. So let's start off. 2 paralleled 50 ohm resistors. Well, we can draw that. So we're going to have a 50 ohm. Let's draw that a bit bigger so I can actually fit it all in there. 50 ohm and 50 ohm. There's our 2 parallel 50 ohm resistors, and they're in series with 3 large resistors of 100, 200 and 250. There's no mention about what order they could be the 100 and 200 beforehand, the 250 after. It doesn't really matter because they would all be equivalent. I'm just going to draw them all after because it gives me the space. So we had 100 ohms. And let's connect that around because I can't draw sidewards to 200 ohms. And let's keep drawing that to 250 ohms. Okay, so we've got our 3 in series. The assembly is connected to a 20 volt battery and an ammeter to measure the entire current. So let's do that. We have an ammeter to measure the entire current, and it connects to a 20 volt battery. Doesn't matter whether we orientate the battery this way or this way. It's much of a muchness. The question doesn't specify what has to flow into. A voltmeter and ammeter must be used to measure the current flow and voltage drop across one of the 50 ohms when a main circuit switch is closed. So let's draw our switch here before we go over to that last bit. Switch symbol looks like this. So there's our switch. And we need an ammeter after one of these 50. So let's draw it after this 50. And we need a voltmeter across it. And we are done. Big complicated circuit, and we could do the same sort of math we've learnt about in class. We know that we could work out the total resistance. We've got the 20 volts that let us work out the current. We'd know the current then going through, or the voltage being used by this and this and this, and then that will tell us the voltage being used by each of those. If we know the voltage being used, know the resistance, we can work out the current. So all this thing is work outable from here. The tricky bit is just drawing it all out, because you've got to pay close attention to detail. Alright, so this is all the one-star questions for chapter 22. There should be another video about the two-star questions coming soon. And remember, though, it will be the subject of your exam. So make sure to have a look at that. Have a good night, and I will see you next time.